Welcome to the second lecture on noise. So in this lecture, we'll discuss about the different sources of noise in integrated circuits, and in detail we'll see about the noise of resistors and MOSFETs, because those two are the main components when we consider an analog integrated circuits. So we'll start with the different noise sources. So if you look at different components in an integrated circuits, we can uh, see components like resistors, capacitors, inductors as the passive components, and we have semiconductor devices like diode, BJTs, MOSFETs as the active components. So when we consider these different components, in these components, these two components like capacitors and inductors, these two are ideally noiseless components. Ideally, these are noiseless components. So we'll not discuss anything about capacitors or inductors. Ideally, they are noiseless. Now, either the resistor or diode or BJT or MOSFET, all these components produces noise, and in our discussion we'll be considering the noise of resistors as well as noise of MOSFET. So anyway, all semiconductor devices will produce noise, and we'll consider resistor noise and MOSFET noise in detail. So we'll be discussing about resistor noise and MOSFET's noise. So we'll start with resistor noise. Yeah, so we'll first look into resistor noise. So in a resistor, basically noise is due to the random motion of electrons. So in a resistor, noise is due to the random motion of electrons, or random motion of electrons introduces, this random motion of electrons leads to fluctuations in either voltage or current measured in a resistor. So if say this is a resistor of value R, now resistor, through this resistor the motion of electrons will be random in nature, and if you measure the voltage or current across this resistor, due to this randomness, or due to the random nature of the or random motion of the electrons through this resistor, the voltage or the current, so if I measure the current, instead of getting a constant voltage as a constant current as say V by R, what we'll get is a varying current. Varying current in the sense it is in a very minute level, but this will definitely affect the performance of the circuit. So this is what we can understand the current through a MOSFET. So there is the expected current is V by R, but along with that we can expect a small noise in the current. But we know that noise cannot be represented with an amplitude or instantaneous value. So we can write the due to this noise, even the voltage will be noisy. So Vn is equal to In into this R. But since it is this representation is statistical, we will represent this as Vn square bar is equal to In square bar into R square. So where this Vn square bar or In square bar is actually the average power, which is expressed in volt square. One another representation, so this is actually average power. So in the previous lecture we have seen there are two methods to represent. One is average power, which is expressed in volt square, and other is actually power spectral density. So that is actually expressed in SVF, which is your power spectral density, which is volts per hertz, volt square per hertz. So the same, the average power measured per unit hertz bandwidth. Now, if you look at the spectrum of thermal noise, it is observed that the spectrum of thermal noise is actually proportional to absolute temperature. The spectrum of thermal noise is proportional to absolute temperature. So if you look at the spectrum, when I say spectrum, what I am drawing here is a power spectral density. So it is SV of F. It is proportional to absolute temperature, and it is actually a constant value across the range of frequencies. And it is observed that this value is equal to 4 kT into R. So so this is nothing but the voltage noise spectral density of resistor. Voltage noise spectral density of resistor. I can write SV of F is equal to 4 kT into R, where this kT is, if you take you just note down this value. This may be useful for solving problems. So it is equal to 4 into 10 power minus 21 with this appropriate unit. So K is Boltzmann constant and T is the temperature. So at room temperature of 300 Kelvin, the value of kT is this one. So your voltage noise spectral density is, it is observed that it is 4 kT R. So similarly, so if I know SV of F, how to write SI of F, which is the equivalent current noise spectral density. So SI of F is actually the current noise spectral density. So since we are writing in this one, similarly, how we have written this. So if I want to obtain SI of F, if I want to plot that across frequency, its value can be obtained as SI of F is equal to SV of F divided by R square. Instead of R, it should be R square, because what we are dealing here is with statistical representation of noise, and it is actually average power. So when I do that, this is equal to 4 kT R divided by R square, that is 4 kT by R. So this is again a constant value, value is 4 kT by R. Right. Yeah. So voltage noise spectral density is 4 kTr and current noise spectral density is 4 kT by R. Now, if you have a noisy resistor, consider this is a noisy resistor, this can be represented as a noiseless resistor. If I want to represent this as a noiseless resistor, then the noise in this should be expressed explicitly with a series voltage source whose value is Vn square, which is the average power in the average noise power in the resistor, or that can be represented as a resistor in parallel with the current source. Which is In square bar. This is again noiseless resistor. Now the current direction doesn't matter, because what we are writing here is the average power, which is square of the current. Right. So this is one very important point. A noisy resistor can be represented with a series noiseless resistor in series with the voltage source, or a noiseless resistor in parallel with the current source. Thevenin and Norton equivalence. Now I'll write down SV of f with the units. SV of f is actually 4 kTr volt square per hertz for a resistor with value R. And similarly, Vn square bar is equal to 4 kTr volt square. So these are the two representations what we discussed in first class, in the first lecture. One is average power and other is power spectral density. So average power is expressed in volt square and power spectral density is actually average power measured per unit hertz bandwidth. So here we can obtain this relation. SV of f is basically Vn square bar at unit hertz bandwidth. Right. So this is also a very important relation. Yeah. So we discussed about the different sources of noise and basically resistors and semiconductor devices, resistors and diodes, transistors, those components are the major sources of noise, and our discussion is mainly on resistors and MOSFETs. In this lecture we have seen the resistor noise. It is due to the random motion of electrons, and this random motion of electrons will leads to fluctuations in the voltage or current measured in a resistor. So with the same resistor R, the current is supposed to be V by R, but we have an additional noisy component which is IN. Now the average power is expressed using this formula, and the power spectral density is observed as 4 kTr when you express as voltage noise spectral density, and current noise spectral density is 4 kt by R. And the kt value is very important. This is very useful in solving numericals. 4 into 10 power minus 21. Now how to represent a noisy resistor in Thevenin and Norton equivalent. And finally the two statistical representation, power spectral density as well as average power. Right. So we'll continue the problems or some numericals on this resistor noise in next lecture. Thank you.